Okay, collision theory and rate of reaction. The collision theory basically states that all molecules or all atoms are in constant motion. So collision theory and the rate of reaction, so the connection here is that the rate of a chemical reaction is proportional to the number of effective collisions per second amongst reactant molecules. An effective collision is one where two particles collide and a reaction occurs. Two conditions must be met in order for a collision to be effective. So the first one is that the molecules have the correct orientation or collision geometry. So the particles have to be angled correctly and collide with the appropriate atom and a neighboring particle. So for this example, we've got NaCl plus a chlorine atom coming together. In this first reaction here, you've got this indicates, these small lines over here indicate speed. So they're moving together and they're going to collide with the chlorine atom and the oxygen atom in the compound. This ends up in a non-reaction, so they just bounce into each other and continue moving towards other species. If the chlorine collides with the chlorine on the compound, so the chlorine atom strikes the chlorine atom on the compound, this is an effective collision, and the reaction occurs. You form Cl2 and nitrogen monoxide. So these are our two products. So here, the first one is a non-effective collision, and it's non-effective because they did not have the correct orientation, and then this one is an effective collision. Before, the middle reaction here is your transition state. So the second condition that has to be met is that the reactant molecules have enough energy to get over the activation energy barrier. So the reactant molecules must have a minimum kinetic energy for a reaction to occur, and it's called the activation energy. At room temperature, many molecules are moving too slowly for this energy to be reached. So that is why we have to heat some reactions, or most reactions. So collision theory depends on the kinetic energy of the colliding particles. This energy depends on temperature. So the more the particles will have higher kinetic energy with higher temperatures. So they move faster when they're hotter. However, activation energy is independent of temperature and therefore will not change with a change in temperature of the surroundings. So you have this minimum amount of energy that you have to overcome in order for the reaction to proceed. That amount will stay the same no matter what the temperature is. So it's dependent on the reaction. A good analogy for this is going 10-pin bowling. You got your ball, you've got the laneway, and you've got the pins at the end. Now, we've been doing reactions before where you just basically bowl the ball down at the pins, try and knock them down. Well, think about it this way. There's a a laneway where it's not flat anymore. There's now a little hill that you have to get the ball over in order to continue down to the pins. So if you don't have enough speed on that ball, it's not going to make it over that little hill, and it's going to come right back to you. If you ever see me bowl, you know that's probably going to happen to me. So basically, you have this energy hump that you've got to get over to hit the pins, which of course do not look like this, but I got nothing else for you. So the ball has to go in this direction. Potential energy diagrams. We did these in the last unit on enthalpy. In a chemical reaction, the potential energy increases as reactant particles approach each other. If the collision energy is at least as great as the minimum potential energy, the activation energy, a transition state occurs. This is also known as an activation complex. It is highly unstable, temporary arrangement of atoms as bonds are breaking and forming. This stage exists for a very short period of time, and a reaction will proceed only if the collision geometry is correct also. So catalysts affect the fraction of collisions that are effective by lowering the activation energy. So catalysts help you out by decreasing the minimum amount of energy that your particles need to have. So if this is, let's say, a potential energy diagram for an exothermic reaction. So here we have reactants, here we have products, here's our delta H. What happens now is there's this minimum energy you have to get over in order for the reaction to proceed. So the only difference here is that you've got this hill to get over first. Your delta H is the same. The position of your reactants and products is the same. Just you have this extra energy, and the difference in height between the reactant and the top of that peak is your activation energy. I'm going to put an F there because that's for the forward reaction. That's going from reactants to products. If you have a catalyst, it will lower your activation energy, so it could be only that high. So in that case, that's activation energy for the forward reaction catalyzed. So there's a considerable drop in energy there. Now, the reverse reaction has a larger potential energy. So all reactions will have a forward reaction. Some reactions will have a reverse reaction. And that reverse reaction is going from your products to your reactants. So one direction it's exothermic, the other direction, because it's the opposite, will be endothermic. In that case, from your products to your top of the peak will be the activation energy for the reverse reaction. So a lot more energy has to go into our system in this case, to reverse the reaction to go from products to reactants. And at the top here, that is where you find your activated complex. Your transition state, where you have both reactant molecules colliding, and they're basically, they come together and make one mesh, one big compound. And it's like it said, it's for a fraction of a second. If you go back to, okay, what does this look like? Carbon monoxide reacts with nitrogen dioxide to produce carbon dioxide and nitrogen monoxide. We know that the activation energy for the forward reaction is 361 kilojoules. We know that the enthalpy change is 226 kilojoules. So that value tells us that this is an endothermic reaction because it's positive. So let's draw a potential energy diagram for this. So potential energy goes on the y-axis in reaction progress or time. Goes on the x-axis. So we know that it's endothermic. It doesn't have to be to scale. So we have carbon monoxide, nitrogen dioxide, and we're going to put in energy, and we form carbon dioxide and nitrogen monoxide. We know there's an activation energy. Okay, so let's label this. Our delta H is 226 kilojoules, and our activation energy for the forward reaction is 361 kilojoules. Now, we can figure out what the activation energy is for the reverse reaction, because the difference will be this amount minus this amount, and that will give us this part here. Now right at the top you have your activated complex, which would be CONO2 all together. All right, so 361 minus 226 is 135 kilojoules. So this activation energy, this is activation energy forward. The reverse is 135 kilojoules. So basically the difference between the activation, the potential energy diagrams that we've done to date is this added part here. Normally the line would continue just straight along here, but now we have this hump, this minimum amount of energy we have to get over. So this reaction is hard to make go in the forward reaction, but it's easier to go in the reverse reaction. And that's because it has a lower activation energy for the reverse reaction. That was 135. So there you go. If you added a catalyst to this, it would decrease both activation energies. Okay, so in grade 11 we did a reaction, and we had hydrogen peroxide. Hydrogen peroxide, you put it in a beaker on the counter, and it just looks like water. Clear, colorless liquid. You don't see anything happening. But then we put in a scoop of yeast pellets. Yeast acts as a catalyst, and the reaction started. We were decomposing hydrogen peroxide to form oxygen gas and water. And the reaction was slow at room temperature. We sped it up by using the catalyst. So in that case, the yeast lowered the activation energy, and there was enough energy now at room temperature in order to let the reaction proceed. You think about striking a match. You need, in order to burn something, you need to light a match first. Where does the activation energy come from? It comes from the friction when you strike it. And that's what gives it the potential energy to catch on fire, which allows you to burn your fuel. So this activation energy has existed all along. You just weren't conscious of it. So there you go. Collision theory and activation energy.